My name is Kyle Rojek and welcome to my exam. So today we're given a problem which has a tube which has a steady stream of air flowing over the top of it. And this tube also contains a liquid composition of acetone and methanol. And we're in this problem, we're also given the vapor phase compositions at the surface of this liquid for the three components in this problem, which is acetone, methanol, and air. So we can say that the surface of the liquid is equal to Z at 0, and where the air is flowing at is equal to Z at delta, which is 0.24 meters, which is also given in this problem. So basically we're trying to find the molar fluxes of both acetone and methanol so that their vapor phase compositions at the airstream are both equal to 0. And in this problem, we're given the Stefan-Maxwell pairwise diffusivities for each of the three components. And I wrote the Stefan-Maxwell equations to save a little bit of time. And so the first step in this problem, first step in solving this initial value problem, is going to be scaling. And the purpose of that is because when we're going from some point to another point on any piece of equipment, we want to scale that problem so that the order of magnitude goes from 0 to 1. That makes it a lot easier on calculations and causes less room for error. So we start this by dividing the length over the total length, which is Z over delta. Forgot how to write delta for a second. And then that is equal to a dimensionless unit, which is eta. So next, we want to somehow plug this into our Stefan-Maxwell equations. And we do that by using the chain rule. So dy1 over dz goes to dy1 over d eta times d eta over dz. And then next, we take the derivative of this function right here in terms of z. And that gives us 1 over delta dy1 over d eta. So next, we want to plug this into the Stefan-Maxwell equations. And we do that by multiplying this delta across the whole thing. So we get dy1 over d eta is equal to y1 2 minus y2 and 1 multiplied by delta over the concentration multiplied by the Stefan-Maxwell diffusivity of 1 and 2. And then we know that the molar flux of air is equal to 0 because there is no air in our liquid composition in this problem. So minus 1 minus y1 minus y2, which is equal to y3 multiplied by n1 over c, the concentration times the Stefan-Maxwell diffusivity of 1 and 3. And so to scale this problem, we want this whole right side of the equation to have an order of magnitude of 1. And to do this, we already know that the vapor phase compositions already have an order of magnitude of 0 to 1. So we need to find an initial guess for N1 and N2 in order for this whole right side of the equation to have a order of magnitude of 0 to 1. And the first step in doing this is moving this delta to the bottom side of our equation. So that we're able to make an accurate initial guess for both N1 and N2. Then we solve for this part of the equation right here. Since we already know the pressure and temperature, which are given in the problem, and also the Stefan-Maxwell diffusivity for the vapor phase. So we know that concentration is equal to P over RT multiplied by the Stefan-Maxwell diffusivity over delta. We can say that is roughly equal to so pressure is about 10 to the 5th. R times T is about 1,000. And we know the Stefan-Maxwell diffusivity for a vapor phase is 10 to the minus 5th all over delta, which can be perceived as 1. And this gives us an initial guess for N1 and N2, which is about 10 to the minus 3rd. Next, we'll be using this initial guess to solve these initial value problems so that the vapor composition of acetone and methanol are both equal to 0 at where the air is flowing. And this was done by scaling